So I'll just start from scratch for those. Maybe I wasn't here actually for the previous tutorials, so maybe maybe it can be just helpful to just start from the very scratch. So you just download the folder, the tarball, we unpack it, and then we go here in the right folder, the DFT TB one. And then from here, we just open up the notebook. So I don't know if it's too small, just tell me and I can just make it a bit bigger. I think the size is okay. Okay, cool. All right, then, I mean, I guess it wasn't that complicated to do these tutorials, these examples, but let me go through it just for the sake of clarity. Maybe, of course, if you have questions, I guess you can also just stop me as I go through it. Okay, so that's basically it. We need to run the SIESTA calculations in the folders. So as I said, I'll do it from scratch. So let's start with the graphene single zeta polarized one, which is the first material. You've all seen already, I guess, the FDF. That's a very simple one, and we can just execute it. Now, I think some of you had some problems with the execution time. Maybe if I remember correctly, this was one solution to just run it like this. And so let's just do it. It's gonna be quite quick actually, because it's not that, it's only a 2-atom unit cell, so nothing too crazy indeed. Now it's over. At least that's on my laptop at least. And okay, so we just go back to the notebook and we read in the Hamiltonian like this. And you can see in this Hamiltonian all of the information. So we are actually reading the FDF file, which is the input file. And this will attempt to read all of the output files from SIESTA, including, for example, the orb index 1, which contains the information about the orbitals. So this information is reported also here when you just print the Hamiltonian object. And as you can see here, this is exactly the order that we need to refer to when we want to select the various orbitals. The index 0 is the s orbital, index 1 is the py orbital. And then you, of course, have also the polarization orbitals because it's a single zeta polarized basis set. And then I guess you're all familiar now with this number of supercell connections, the lattice vectors, and that's basically it. Now, so now with this cell, we can just plot the band structure, take a look at it. It's the usual one. In this, you can see that to do that, you just need to create this band structure object. You can set here the high symmetry points that you want to see in the plot, the number of energy points, the labels for the high symmetry points. And then with this, you can get the linearized K points that you can use in the x-axis in the plot, along with their labels. And just by doing this, you can get the eigenvalues for your Hamiltonian. And then the rest is only plotting commands, nothing too complicated indeed. And so that's the bands, the usual ones. And now we want to know whether we can reduce the size of this Hamiltonian into a smaller one just by projecting it onto a limited amount of orbitals of this basis set. So whether we can get a correct band structure just by retaining only some of these orbitals in the 2 atoms that make up the unit set. As you can see here, the the number of orbitals, the total number of orbitals in the unit cell is 18. So let's see if we can just make that smaller. And in order to check whether we can do that, we can plot, for example, the orbital projections to the various eigenvalues in the band structure. And this is a way to do that. It's actually quite so it shouldn't be that complicated to. So we can go through it maybe just very quickly. If you have not, some of you have doubts about it, just ask. So this command allows you to get the orbital indices, the orbital index for the first orbital of each atom in the geometry. That you can do it like that. So this is a list with containing the index of the first orbital, so the s orbital for all atoms in the geometry. And then by doing this, for example, so you can just sum 2 to this list, this array, in order to get the indices of all pz orbitals for all atoms contained in the unit cell. Maybe to just make that clearer up here. So how to choose these numbers like 2 or the indices for the s, p, x, p, y, pz orbitals. I mean, we can just actually you can just count the orbitals by looking at this. That's just the easiest way, of course. Otherwise, for example, if you want to have like a clearer image, clearer view of this, you can just loop over the atoms in the unit cell. So you can do it like something like this. I think it was something that Nico had written in the Discord channel. So let me just report it here, which is actually useful. You can just do it like this for each atom. You just also loop on the orbitals in that atom. And then you can print information about this. So for example, we can print the symbol of each atom just to see what we are seeing, the index of that atom, the index of the orbitals in that atom. And then, for example, we can get the quantum numbers for each of the orbitals like L and M. By doing this, I actually wrote something wrong here. By doing this, you can see that we have 2 atoms in the unit cell. That's the same information written here nicely. Now we can just get the numbers, the indices. And as if you remember, the third column is the index of the orbitals for each atom. You can see that there are 9 orbitals, and the pz one is the one with the L equal 1 and M equal 0. So we need to select index 2 if we want to take the pz orbital out of the Hamiltonian. So, but this is an information that you could immediately get just by looking at this, which is the basis set with the names for each orbital in the printed stuff itself. So just to so that's why we place 2 here. So it's 0 plus 2, for example, that makes 2. That's the pz orbital for the first atom in the unit cell, and then so on and so forth for the other atoms in the unit cell. And by doing this instead, just by using some Python broadcasting, you can also get the indices of the s orbital, the py orbital, and the px orbital. By doing this, you get all of them inside this object. And now this is a trick is a way to project the eigenstate onto, so to calculate the weight of each orbital onto the eigenstates. Actually, not of each orbital, but just of either of these ones or of these ones. And you can use this function as an option to the eigenstate call down here to wrap the information about the 2 lists of orbitals and get directly the orbital weight summed over all of the orbitals in this list and in this list, which are these 2 objects, along with the eigenvalues themselves. So after we do that, I don't remember if I executed the cell. No, I think I didn't. That takes some time. Actually, so you also see that there's this warning, and that actually comes from the fact that there's some so it's all orthogonal states in the basis. So this won't be used when plotting the fat bands. The imaginary part, anyways, is not going to be used when plotting the fat bands. So we don't care about it. But I think that's just a simple solution to avoid that is to just take out the real part of this object here to avoid that. Since we know, anyways, that the orbitals are orthogonal. So once we do that, let me see if there are some questions. Just speak out if you have questions, of course. Otherwise, I just go on. Now, this is instead the way to visualize it, and that's actually quite simple. It's like visualizing the band structures, just with the with calls to fill between in matplotlib to get the colored bands with a certain width, which is proportional to the weight of the specific orbitals that we have selected with respect to all of the other ones. And as you can see here, for example, we have done this for the in gray. You can see just a generic band. We fixed the width for all orbitals and show it in gray, overlap to the bands. And instead, the contributions to the PZ orbitals, we showed them in blue, and the S, P, and Py in red. And you can immediately recognize the pi bands, which are contributed mainly by the PZ orbitals, and the sigma bands, which are contributed by the other three ones. But still, there are some other orbital contributions in the unoccupied energy range. And that's why we will see actually that the projection onto S, Px, and Py will qualitatively reproduce the features of the bands up here, but not quantitatively, because they will be energy shifted up. But we'll soon see that. Here comes the core of the example of the exercise. So this is what you were actually supposed to do by yourself, indeed. Let me just do this. So if we want to use this sub-orbital command, which allows to project the Hamiltonian onto a subset of its orbitals, we need to know how to do that. And it is simply just written in the documentation. Should be clear that we need to use as a first option in the command either an array of atomic indices, 0, 1, 2, blah, blah, blah. In our case of graphene, we can only use, for example, either 0 or 1 or 0 and 1. 2, there's no atom with index 2 inside the geometry, so that would not work. So we can either use such an array, or we can directly provide the atom object, the caesal atom object in the geometry. And that's something that we do in this way, just by selecting from TSHS the flag at the object's atoms, which will return a list, in our case, of just one species. So we just take the index 0, because there's only carbon in the unit. And now, here, for example, we assign that to this to this variable C, and we can immediately write here that if we want to retain PZ orbitals from carbon atoms, for sure we need to use C here, and also C here. That's for the S, Px, and Py projection instead. When it comes to the second flag, now that's also an array-like object in Python, or an orbital directly. And that's exactly where we need to put the indices of the orbitals that we want to project on. we already know those numbers because those are the same that we have used up here. So this is for the SPX and PY. So we can just take it. And this is the one for the PZ. So we just go down here. We write 2 here for PZ. And we put this list down here for the other orbitals. And we can see that by printing out atoms, it can be seen that now this Hamiltonian contains only a species which is renamed C2, just to recognize that this has been projected onto orbital index 2. And that's where we can check that it actually worked, basically. So we can see this. Also, there are no other, so there's no other orbitals. One more way to do that is just by plotting, for example, the number of non-zero elements, for example. And you can check, for example, that that's now been, that has been reduced with respect to the TSHS. So if we do actually this, you can have you can easily compare the situations here. So you can see down here that there were 5,994 non-zero elements in the Hamiltonian at the beginning in the TSHS object. And now by extracting only PZ, there will only be 74. So that's quite a reduction. And 666 if we project onto the S and P and PY. So now we can plot also the bands of these 2 Hamiltonians on top of the DFT bands. And we can do that with this cell. So that's just a convenient function that we can call over and over again, just by after defining the band structure object that we were seeing in a previous cell and providing the Hamiltonian. That's exactly what it's done right here. So band is the one for the that we calculated up here. Well, right here, band. So that's exactly this object. And we can simply now execute the cell to see what happened to the bands. Interestingly, you can see that inside this, so we don't need to redefine the band structure object in Python because this function here will update the parent Hamiltonian for the Brillouin zone, for the band structure that object that is being set up in SIESTA. So that's actually quite useful. You just need to call in one line, and you'll get everything correctly. So that's how it looks. And that's what I was showing in the slides, for example. Some of you might have noticed that indeed that it's not a perfect reproduction of the DFT ones. That's because of the fact that some orbitals might still have some contributions. For example, around the endpoint here, we could, for example, try to, and the same thing happens in the signal bands, where you can see the energy shift that I mentioned earlier for the unoccupied part. But you can see that, for example, just by you can play with the with the indices of the orbitals and try to get something that can fix it. And for example, I don't know, one option could be to just introduce some more orbitals, like polarization orbitals, for example. And just to check it all together, we can, for example, I don't know, use one of these ones. So all index atoms with L equal to down here, so 4 to 8. And we can try just to do that to see what happens. For example, say we can try with the 4 for the PZ. And in that case, would that help? Absolutely not. That would just mess it up. So that's not the solution. Instead, with 5, we can get something that we actually don't see any relevant change. We can try with number 6, which just adds some more bands, but it doesn't really help with the pi bands, so we don't really like it a lot. We can go on with the 7. And that's exactly what we needed to fix the bands around the endpoint. So index 7 is actually associated to the, I think it was this one. So it's the dxz. So it's an orbital with the x with symmetries along x and z, and that seems to solve the issue. So that's basically it. You can just play with the orbitals and try to get the DFT bands. Now that's obviously not always an option. This was a super easy case, the graphene one, and there were. I mean, one always needs to just try and see whether some bands can be reproduced. And one needs to do that either by, one can check that by plotting the fat bands contribution, as we did up here for the material of interest. But also just by, I mean, if the basis set, I mean, it's not that the basis set has so many orbitals per atom quite often. So, I mean, one can also just try and try with different combinations of orbitals and see whether that can work. Of course, doing the fat bands can just save time sometimes. But yeah, so but that's not obvious. So that's one thing that needs to be clear, because this is only an extraction of basis sets from a basis set which has where each orbital has a chemical meaning. So and we are not modifying that chemical meaning. So the symmetries of the orbitals are retained, that we extract they are retained. So we don't optimize the basis set in any way. And that's why sometimes that cannot really reproduce the bands perfectly, as you could, for example, do with other tools, like, for example, Vanya 90 or something like that. But as you can see, if you are studying a system where this can be done, then using this command is extremely convenient, because it's just one line of code. And yeah, so that's basically it. I don't know if I should go through actually the rest of the exercises. It depends on how much time we have. What do you guys think? So there's questions. There's questions. Let me see. Well, so I think I can read the Hamiltonian from the FDF. So Raul asks, I can read the Hamiltonian from the FDF file in this case only because I asked SIESTA to write it. Well, I'm not sure what you mean exactly. That's so you can read the FDF file. Of course, let's say it like this. You can get the Hamiltonian by reading the FDF file, of course, just after you have run SIESTA to execute the calculation, of course. And that will internally look for the other files that define your geometry in your system, like the orbitals information and everything else. But maybe I'm just misunderstanding the question. So please maybe, I don't know. So, okay, so this other question, there's Xavier. He is asking, I think Caesar checks the FDF file to see. Okay, this is actually the question, the answer that I gave, and then goes to such file to the Hamiltonian. The FDF file itself does not contain information about the solution of the calculation, but all the input parameters to perform. That's exactly what that's exactly it. So Xavier is perfectly right. And that was just a waste of time. I didn't read the question, the answer by Xavier. And Mez No, who's I can see the name. Yeah, it's Mets. Did you just add DZX and got the good agreement? What about DYZ? Okay. Where is it? We are talking about, yeah, so here. Well, that was just a trial and error, to be honest. I have to admit that I never tried that before, but that's so 7. I think that's exactly the one that number 7 is the XZ. Yes, and go with it. What about the YZ? So the YZ was this one, and let's just try to put it back again. So it's 0, 1, 2, 3, 4, 5. And let's try with number 5 once again, just to see what was the result. Number 5. So it seems that didn't really help. So yeah, I'm not really sure why, because both of them have symmetries along Z, actually. But yeah, maybe we can chat about it. I don't know if you are listening, Maz. I guess yes.
Yeah, I'm listening.
See.
Yeah.
Okay. Yeah.
Just,
so I don't know. That's
just funny. I don't know.
Yeah, I agree. I don't know why either.
I would guess that it was correcting half of it, kind of, and then you need the other half. But I don't know. That's interesting.
Yeah. Yeah, indeed.
Maybe the okay. Maybe it's because the structure is breaking the symmetry, so it's the bond. No, I mean.
Oh yeah, maybe.
No,
maybe.
No, that's strange. But I mean, it's interesting if you can just add one and get it.
Yeah, indeed. Indeed.
In principle, I guess, because I mean, you don't care about the part which is in the X. It is, I mean, in a sense, it's okay that you should just add one. I just don't see why it's okay just to have the
just
X
to do it
one.
With the X Z and not the Y Z. Try
Yeah.
both, Nick suggests, but I guess with both,
yeah, then it should
work,
yeah.
Right? I can't see why it should. Yeah, you can actually see some more contributions up there. Actually, I could try to plot it just on a larger energy range to see. But yeah, I mean, 7 seemed to be already fine. Yeah. So, but I don't know, maybe if it depends on how much time I have already. Just Nick, how much time do I have? So maybe I can go through, for example, exercise number 1 and just write it down right here in the notebook. Should I do that?
Yeah, I don't really mind. I mean, we just have, I was also crossing the time a little bit. We have Sophia up next. I think it's at 11:30, right?
Yeah, I see.
But that's it.
Maybe I can just go through the first one, or just let's just take a break and before Sophia's one.
That's fine if that's.
It shouldn't be that long, right, to do this.
Oh, that's true. Yeah.
Because
so quite fast, yeah.
I mean, the first exercise was just asking, like, just to check what's the difference with the first nearest neighbor model, and I mean that's if we just go and do that. Okay, so exercise 1, and we just go here. So we need to define the geometry for graphene first of all, and that we can do with this simply just by doing this, and then we can define the Hamiltonian for graphene. Let's call it for first nearest neighbor. For a nearest neighbor graphene Hamiltonian, that we just define it as just like this. I can't remember if it was already default to do it orthogonal. But well, we can check it actually just by doing this. Let's just check it. I think it was orthogonal optional. Is it equivalent? I can't remember if it was default. Maybe it is. Oh well, that doesn't really matter for now. So see, that's the Hamiltonian. Now it's an empty Hamiltonian because we need to. If we visualize it, you see that there's not zero non-zero elements. So we need to construct it, and that we can do just by doing like this and setting inside the radius list and the Hamiltonian parameters list. So within 0.1 from angstrom from each atom, that's the elements that we. So that's the diagonal elements of the Hamiltonians, and then we just set these on-site elements to 0. And then instead, since it's 1.42, if I remember correctly, the bond length in graphene, we can say that all atoms within a radius of 1.5 angstrom, they need to be coupled together with a 2.7 eV hopping parameter. And now I think we also need to assign that. No, we don't need to do anything like that. So just by doing this, we'll already construct the Hamiltonian. As you see now, there are 8 non-zero elements in the Hamiltonian. And now we can just, for example, plot the band structures together conveniently just by doing this, something like this, for example. So without of course, without the function, because that's already defined up there. We don't need it. And we can, for example, just do, I guess, this and plot it like in red, for example. Like this. Let's see if that works. That worked. And so you can immediately see here that the first nearest neighbor type binding model works pretty well, very close to the Fermi energy. But as you go farther away, you have distortions with respect to the DFT one. And that's that was maybe trivial to show, but I mean, when most of there's so many works done with the simple nearest neighbor type binding model for graphene. And just so you know that they use this kind of models. It's most of them focus on Fermi level properties, for example, but it depends on the study, of course. For graphene, maybe it's not that important because qualitatively, more or less, that's it. But if you're interested in having a band structure which closely reproduces the DFT one, then it might be crucial to just project it onto these orbitals up there. Okay, but that's this exercise. Maybe I can just maybe mention how to, because maybe that was something that people didn't really that maybe some people had difficulties with it. But just to be super clear, if we try with the exercise, I think it was exercise 3. I'm not going to just go through all of it, but just to I just wanted to say that, say, for example, you have a material with 2 species. Then in order to extract on different species, for example, let's say we do it for MOS2, and imagine to read the Hamiltonian for the MOS2, you will find that this that sulfur is the second species and molybdenum is the first one. So you just get them like this. And if you want to imagine TSHS is the Hamiltonian, we want to get, for example, an H which is smaller, just call it small, and with a reduced number of orbitals. And to do that, we can, so if we just do sub-orbital on MO, and whatever set of orbitals, so say the S, and then the D ones, which are 5, and it's the first 5 ones. Then by doing this is just not enough, of course, because, or at least what this does is just to retain all orbitals from sulfurs in the geometry. And for all molybdenum atoms, it will only retain these orbital indices and exclude the other ones. So that's what this would do. If you want to do this and also restrict the orbitals for the sulfur atoms, you need to do it sequentially by doing something like this, for example, and then choose whatever you want here, say the S and the P orbitals that are the first 3 ones. So by doing this, you're actually retaining the S and P orbitals in sulfur atoms and S and D orbitals in molybdenum atoms. Now, if you go through the tutorial, you will have a chance to see whether this is enough to reproduce the features of the bands close to the band gap of MOS2, or whether you need some more orbitals to be included in the basis set. But just to tell you that if you have more than one species, you need to do this sequentially. And one last thing, and then I'm just gonna stop. If you just want to use, if you just want to retain one species and completely remove the other one, you can also do that. And in order to do that, you will first have to do a sub onto MO only. That will create a geometry which contains only molybdenum and an unused atom class for sulfur. So if you just go and plot this Hamiltonian, you will see that it will be 0 sulfur atoms, but the atom class will still be there. So in order to remove the atom class that is empty, you can simply do this. And after that, you will end up with an HMO, which contains only molybdenum with all its orbitals. And if you want to just restrict now this Hamiltonian, you can simply go on and do something like this. So a suborbital onto HMO for MO species and only these orbitals. So that's basically how you do this. And but maybe I will just put some more comments and maybe just go through all the exercises and so that the notebook that we upload is full with all of the solutions for all of the exercises. Maybe that could be, even if I didn't manage to do it on time here, I can just do it and you'll find it online. That could be an idea, maybe. There's some questions and then I stop. That's why, Alexander, I think that was about the symmetries. Alexander was suggesting that maybe it's because graphene is symmetric around the y-axis and that the DYZ has different parity along y compared to PZ and DXZ. That could be a solution indeed. Anxiety, may I ask a question not specific of the exercise, but more related to the application of this method? Of course, you can ask, definitely. But maybe it's easier if you unmute yourself and just speak out.
Yeah. Hi, Dano.
Yeah.
Yeah, I was just wondering if, I mean, we can build a large sample from a DFT calculation using this is really useful in that sense. But let's say we perform a calculation, a DFT calculation of our unit cell, and then build that large sample. But let's say we then want to sandwich this sample between some other electrodes. And I guess we should do another SIESTA calculation to figure out what is the Hamiltonian of that interface, right?
it depends. I mean, if the electrodes are made of the same material as the scattering region, then
No, yeah, from
you
a material. Let's say we do a nanoporous graphene sample and we want to sandwich these between two graphene electrodes.
So well, that's not trivial indeed, because then you cannot just have a device region which contains MPG nanoporous graphene and just attach it to pristine graphene electrodes. You need to include inside the scattering region some parts of the geometry which look like graphene, and on which you can actually unfold the self energies for the graphene electrodes. Otherwise, you can really run the the transport calculation with that. So what you can do, I guess, is just to make a periodic DFT calculation with a geometry which has a nanoporous graphene in the middle, and on top and bottom, for example, has graphene, and it's periodic. I mean, it's you just do a calculation for that. Then you read in the Hamiltonian for this periodic system, and you parameterize this one and store it as a device region. And then you should, I mean, I guess depending on, I guess you can just take out the parameters for, if you make the graphene region large enough, you can just take out the parameters for the electrodes directly from this calculation, like as a sub part of the Hamiltonian, and store them as electrodes. And at that point, you will have an NC file for the device region, an NC file for the electrodes, and you can run a TB trans calculation with that. That's doable. But you need to, I mean, I don't know if it's clear or someone else has something to say about it.
Yeah, maybe I can. So this complicated thing about extracting some orbitals on some of the atoms. I mean, since CIESTA allows you to do this on sub-atoms, so only on a subset of atoms, this allows you to retain the full complete Hamiltonian on some of the atoms. Say if you, in the nanoporous graphene case, if you had some of the like you had in your poster, some of the benzene rings rotated, what you would need to do is retain a much larger degree of the orbitals on those subparts, but also on those that connects out. So you would just reduce your orbital size such that you still retain the same physics. And you can do that atom by atom to figure out how you can actually parameterize it in the correct way without destroying the physics. So then you would still, in the leads, only retain the PZ orbitals, for instance, but close to your rotated benzene rings, you would just retain both the PX, PY, PZ, and possibly some D shells if that's needed.
Yeah. Okay, yeah, I see that point. Yeah, so then I guess.
But what?
Yeah, one should do the
SIESTA
calculation for the whole device, right? Like including your electrodes and your scattering region. Like there is no way of doing a pristine nanoporous graphene calculation to extract the DFT tight binding parameterized Hamiltonian and make it as large as you want, and then introduce some interface to the graphene electrodes. I mean, some DFT tight binding.
That's the point. That's the point. That's one important thing I think that needs to be, because that's an ongoing, actually, it's an ongoing discussion that we're having also with Nick regarding the possibility of attaching and appending Hamiltonians in CIESTA, for example. That's not trivial to just append them any two Hamiltonians which are different from each other, because of you need to know how the couplings between orbitals of one system and the orbitals in the other system look like. And if you do two separate SIESTA calculations, you will have periodicity. And then the couplings in the nanoporous graphene calculation, the couplings will be between nanoporous graphene orbitals and at the boundaries. and in the graphene one, they will be between graphene atoms. So you need it somehow to do something about this. But that's really a powerful thing. We're actually discussing in the last weeks about this, because that would allow indeed to just make two small DFT calculations, one for one material and one for another material, and then just read them in CIESL, tile each one of the systems as you wish, and just if you can stitch them together, then you can do many things, of course. But it's not trivial. It's not trivial, and I mean, Nick probably hates us because we have been asking him for so long to implement something like that. It's not trivial, indeed. Yeah. So, for example, in the nanoletter article on the nanoporous graphene that I was doing, if you remember, we were doing some hybrid calculations with like different types of nanoporous graphenes, like say the para one and the meta one stitched together. But that was indeed just a nearest neighbor model, not parameterized from DFT. And that's because we weren't able to retrieve from DFT the couplings between the para and the meta, unless we were doing some interface DFT calculation, but that would be periodic anyways itself. So it's not super trivial, I would say. I think that relates more to your question, right?
Yeah, exactly. It was something I was just wondering the last days, and it doesn't look trivial. That's why I asked this question. but thank you.
Welcome. I think maybe we can just take a break, and then Sophia can go with the tutorial, right?
Yeah.
Thank you.
Let's do that.
We can wait maybe